at the University of California, Los Angeles, at UCLA, and she's working on the properties and dynamics of ionized and molecular gas at the center of the galaxy in the vicinity of the supermassive black hole. There you go.
Thank you, Rainer, for the introduction, and thanks for having me here. I'm very happy. This is my first time here in this institute in Granada. It's a gorgeous city. So I'm very happy to be here and to talk to you about my work. So as Rainer said, I am at the UCLA Galactic Center Group, and the work that I will be presenting to you today is done in collaboration with also Randy Campbell at Keck Observatory, so that's why we have both of the logos. So what I'll be talking about is about our galactic center, and especially about the interstellar medium that is located there. We hear very much about the stars, but there are a lot of interesting things to be done also with the interstellar medium. So here is a very short outline. I will just give a very brief introduction on the galactic center and just go into the data set I've been using, the way I'm analyzing it, the results, and if I have time, and another interesting technique and some other fun stuff you can do at the galactic center. So let's get started right away. It's a beautiful infrared image of the galaxy. The galactic center is very easy to spot. It's right here, very bright. So if we zoom in at this point, this is a HST image where I'm just showing the bright stars, but what you have here is the stars. It's very crowded, it's very interesting, it's very energetic. And if you want to study this region, we need very high resolution. And what you find is some just cluster where you have a lot of hot early type stars that emits a very strong UV radiation. So the question is, we know that the center of our galaxy is a supermassive black hole, so how can all these strong stars form there? It's not yet completely clear. So to study the stars, you need to go and zoom in more. So this was the HST image. Here is the image taken by the imager 2 and the L-band. We see the stars and some gas features better. And then if you really zoom in this very inner part and you look at this area, every year after year, you will see the stars moving. That's how you create this nice movie. Well, all these blocks are stars moving observed since 2003 up to 2017. So you can start the orbits of things orbiting around the center. And thanks to this, we can measure that at the center of the galaxy, there is a source that very probably supermassive black hole with 4 million times the mass of the sun, and this mass is concentrated in the one part. So it's a very interesting region. I think I cannot it's a very interesting region, very energetic. The stars tell us a lot, and it's very interesting because there is a supermassive black hole that is closest to us, of course, because it's our own galaxy. So these are the stars. A lot of them tell us a lot, but these are not the only thing that you have there. If you look now at the same scale as gas, you see something like that. So at this scale, the interstellar medium mainly is distributed to two different structures. The circumnuclear disk, or CND for short, that you see here in red, is this lumpy, ugly red ring with an ionized cavity composed of molecular gas, dust, and instead of heavy, you see this structure, this spiral structure that we call the spiral, that is composed mainly of ionized gas. So these structures are there, they are evolving, we don't know exactly how they form, and there are a lot of general open questions on the galactic center. How does this young star form in such a style environment that is a black hole, and how these two structures influence and how they evolve?
So interstellar medium is interesting because it can help us understand a lot about this complex environment. For example, interstellar medium can fool star formation, it can accrete on supermassive black hole itself, it can trace in general processes like shocks, stellar interactions, and so on. So this is a unique environment that we can study because it's the closest supermassive black hole that we have, and also because it's a unique chance we have to look at the interstellar medium and how gas behaves in such an extreme environment that we cannot really reproduce or observe anywhere else. So how do we observe the galactic center? We can do it in many ways. A very nice way to do it is using the Keck Observatory, and this is the observatory from where all the data we presented to you today is coming from. It's in Hawaii, it's a 10-meter telescope, and of course to observe the galactic center you need very high resolution. Since you are on Earth, you need to compensate for the effect of the atmosphere, and thus use adaptive optics. So here is the field of stars that we see at the very center of the galaxy. When you don't use adaptive optics, you see a bunch of blobs. It's very hard to look at them. When you use adaptive optics, you see something that is much clearer, and you can really follow the stars as they move around. Otherwise, you really can't. So this is the power of it. But of course, we have a lot of data. So we have, for example, those two fields, they cover the CMD, that are done with a collaboration with the Observatoire de Paris, and this is a paper that is in process. Then we have a lot of fields that cover various patches of the inner cavity. And the most interesting thing is we have the very central field where you observe the star moving. So this field have you observed every year, multiple times a year for 12 years. So this is great because this is not just data, this is spectroimaging data. So we have imaging and also spectroscopy information about all these areas. And for this very central one, we have it repeated year by year. So we can know a lot and create a map at high resolution in many lines of this central parsec. And also we can observe the gas and not only the stars as they move around supermassive black hole. So basically my work is about recycling data, has been used to study the stars and create this beautiful movie that I showed you at the beginning, but use it to look at the gas. Okay, we are in the infrared. This spectroimaging instrument is called OSIRIS. So this is an example of the data you get from OSIRIS. So it's spectroimaging data, so the result that you have is a data cube where you have 2 spatial dimensions and 1 wavelength dimension. So it means basically that in your field of view, for each pixel you have a corresponding spectrum. Also it corresponds to the fact that for every wavelength you have an image. And this is what is shown here. So this is the field I showed you before. This is how big the OSIRIS field and mosaic I'm looking at is. So it's really in the vicinity of the supermassive black hole. Here you have an image at one specific wavelength taken out from this cube, and this is an example of a spectrum extracted from it. So it's infrared band around 2 microns, and you have, for example, here the emission line coming from a star, and here the absorption line from a star, and what I will concentrate on is the emission line, bracket gamma, coming from the gas. So the ionized gas in this case. So how do we do that? So the first problem is that, of course, the galactic center is very crowded, and this kind of data is very complex because you have spatial and spectral information. So how do you disentangle all this information and try to make sense of what you have? It's complicated, and at Keck, Randy Campbell, with whom I have been collaborating, have developed this very nice tool that helps you look at your cubes with all the dimensions at the same time. This tool is called Ostrus Ball. It's a bit complicated to pronounce. It took me 2 weeks to manage to pronounce it accurately, but now I can. It's going to be available soon for everyone that is interested. You can read CAC data, but also VLT data. So if you're interested, just talk to me later or write to Randy. So basically you see all your dimensions at the same time. So here we have our spatial dimensions, and here is the wavelength dimension. So it's pretty messy over here, but I told you I want to concentrate just around bracket gamma emission line that is over here. So we can cut with this tool directly or with some script a cube around the line we're interested in, and of course in this way you see all the continuum coming from the stars. So in order to put out the information about the gas, you need to subtract the continuum of the stars, otherwise you don't see anything. You're kind of a fog made by the continuum of the stars. And here is what you get when you subtract the stars. So you start seeing structures, both blue shifted and red shifted, and there is a kind of a plateau of probability foreground emission at kind of 0 velocity. And here is just the 2-dimensional view of the stars, and when you subtract the continuum, you start seeing all these filaments of gas and so on. So the problem is that the cube is complicated, but with this tool you can actually turn your cube around and try to follow all the structures you're interested in. For example, you want to look at this one, you can see, okay, it's red shifted, and I can disentangle it from something that looks like it's foreground and so on. So this is a very funny game to play. You pick up your structure, you turn your cube around, and you can understand if it's just one structure, it's multiple structures. It's very easy to visualize this way. If you ever use it, be careful, it's very addictive. You can spend hours turning your cube around and looking for tiny structures. So this is just another view. This is the classical view, image view, and spectral view. So you have X and Y here, and here you have Y and lambda, just to show the cube in a classical way. Another thing that you can do with this cube is color the part of the spectrum that are red shifted and blue shifted, so everything that is in this part of the spectrum is blue shifted, and this is red shifted, of course, and this helps you also disentangle all this tiny structure that you can have in this environment that, once again, is very crowded. Of course, I told you we have all this observation year by year for 11 years, so it's very interesting when we want to try to trace the movement of the gas, but the problem is that, of course, all the observations are not perfectly aligned because the pointing of the telescope is not perfect, so you have, if you want to make something that is precise, you have to align these cubes, but in this field, everything is moving. It's very hard to make, but with Astrofísica, you can charge multiple cubes at the same time and try to align, so it's helpful. You can visualize many of them at the same time. Even if you have multiple images from different parts of the sky, you can put them together this way. Okay, so thanks to this cube, after hours of turning the cube around, I could point out some structures. Some of them have been already observed, some not. So here you have the image view and the spectral view. So again, this is X and Y, north is up, and here you have Y and lambda. So it's when you turn your cube this way. So there are many structures in here. Here you have a supermassive black hole. Here you have some filaments that we could also see at the beginning. This complex structure is called epsilon structure. But what I will be concentrating on for the rest of the talk are mainly this structure, X7, that is kind of elongated, Z, that is right next to it, V and W that are very close to the black hole here. So here this corresponds to X7, the elongated one, that is blue shifted. V and W, those two are blue shifted as well. On the other hand, Z is the only one that is red shifted. Okay, this is an easier way to say what I just said, using the tool that is in Astrofísica, where you can color what is blue shifted and what is red shifted. Here, everything that is red is red shifted, what is blue shifted, and what is purple is more or less at zero velocity. So you clearly see that X7 is blue shifted, those two V and W also, and Z is red shifted. Okay, so all these blobs sometimes have been observed before, so we can also compare with other bands. For example, in the radio, with this paper from 2016, we can recognize part of X7 here, Z, V, and probably W, even though it's a bit messy here. Also, most of these stars are also infrared source that we can observe also in L-band images. This is an image taken by by Keck as well, but with the imager near too. And we can recognize again X7, maybe Z, V, and W. So maybe there is not really a counterpart in this case. But this helps us understand what these things are, if they have other counterparts, other bands, how they behave. So I just told you before that this observation has been taken every year, and then I take good care of trying to align them one by one thanks to Astrofísica and knowing the movement of the stars that we know from the orbits and so on. So we can build a movie that looks like the one I showed you before about the stars. It's not as fancy because, of course, for a spectral imager, you don't have the resolution, the spatial resolution that you have for an imager, but have a look at the movie now. I think it's a lot of fun to look at. The alignment is not completely perfect, and anyway, everything is moving in this field, so it takes a while for your eyes to get used to it. So what I want you to look at is this X7 source here. You look at it, it's kind of stretching and moving towards the black hole, Sagittarius A star. Z here is moving kind of behind X7, and the other two are kind of hard to see in this movie. I will show another movie. So this is all the spectrum, but just to make sure you see better all the blobs, I show you this movie where we are just looking at the blue shifted part of the spectrum. So we don't see Z anymore because it's red shifted, but we see X7, V, and W. So if you look at X7 again, it's very nice because it's kind of a tidal feature that is moving toward the black hole. Maybe it's going to accrete on it, it's not clear. Then you look at V. Look at how fast it's moving from here up to here in 10 years. It's very interesting. And W is moving on the opposite direction, kind of going away from the black hole. So all these are interesting blobs. Yes?
The spatial scale here is comparable to the one shown in the movie of the stars?
No. It's larger actually. The stars, I think, is like this. Yeah, it's kind of comparable. It's slightly bigger. Yes, I'm sorry, there is no scale. I tried to show you at the beginning, but it's hard, you're right, to keep in mind how big the scale is. But this is all very close to the black hole finally. And if we could trace the orbits of the stars, we have, for example, one of them that makes like this, and some other like this, and so on. So these blobs are interesting, but we don't know exactly what they are. Are they just gas clouds, or they have a star inside? Are those like this G2 object that people from the Galactic Center have been talking about a lot? So this is the information about the proper motion that we get from the movie. This is just basically a summary. The arrow is just showing the direction they are moving to. So we know that X7 is moving toward the black hole, Z as well, V as well, and W is moving away. And we also know that X7 is stretching out. So this is information about the proper motion, but also we have the spectral information, so we know about the velocity. So now we are looking at the Y and lambda part of the cube for X7, the blue shifted feature. And it's, this feature is just encircled in this blue circle. And you see it so in 2009, 15, and 17. And you can see that it's, at least part of it, the part that is leftmost is slowing down. So it was a bit left on the 2009, and when you look at it, it kind of look like it's going towards the lower velocities. So it's interesting also to notice that maybe there is a structure in velocity for this feature. And Z, the redshifted one, you have it here. It looks like it's moving toward the black hole as well. We saw it before, and we don't see a lot of changes in velocity for this case. This is W, the one that looks like it's moving away from the black hole, and it looks like it has a constant motion. And this is V. And V is very interesting because, so if you remember, it is moving away from the black hole, but also it looks like it's really slowing down. So there is no circle here, but you see it here. So in 2009, 15, and 17, you really see how it's approaching the zero velocity. And you see in the upper plot here, it goes from a negative velocity of 500 to negative velocity of 250, so it's slowing down. And you see it also in its emission line here, year by year, that is slowing down. So when you put together the information about their proper motion and their velocity, you can start thinking about the orbits of these things, if they are on an orbit, of course. So we can, this is a very schematic, very simplistic image of how these blobs could move around the supermassive black hole. So X7 maybe is coming from behind and is going toward the black hole. The same thing for V. And Z maybe, since the redshifter is coming from foreground going behind the black hole. And V looks like it's moving away from the black hole. So the question is, for V, for W, has it already passed to the closest approach to the black hole, and then this is an interesting information. If it survived, then you have to have a star inside that keeps it together and prevents it from getting destroyed by the forces of the black hole. So this was just imagination. Now we can start really fitting the orbits, and this is just an example. This is preliminary, something that I'm doing right now. You take, for example, V and W, and you have here the arrows and the orbits that is fit here, and you can get the eccentricity, the period, and all you need to know about the orbit. Of course, this is just the beginning, so it's very preliminary, but it looks like, for example, V has a period of 200 years, more or less, and not a very eccentric orbit. Now, I showed you that we got some proper motion. Some of these proper motion studies have been done before, for example, in this paper from Eckhart et al. 2013, where we have, for example, V2 is our V. Sorry about the confusion in the names. D4 is X7, D3, it's maybe W, it's not very clear. But as you can see, this proper motion that they get for X7 is not quite the same that we get, but it's maybe because we don't have actually the same span of observation. These are calculated from 2003 to 2008, and we have observation between 2006 and 2017. So maybe it's something like that, but we also have a very huge data set thanks to the fact that we also have spectral information, so we can really get more information about orbits and the movement of these things. So, just a few more words about X7. This is another paper that talks about X7, where they use the L-band images in Music et al. 2010. And you can really beautifully see in this L image that this feature X7 that we have here have what looks like a cometary shape and looks like there is a bow shock. So that's a very interesting feature. This up here is the movie that I was showing you before. It's not working, doesn't matter. That this feature, we also see it stretching a movie. We don't really see this cometary shape, but it's very challenging and it's very interesting to try to understand what it is. It's just a gas cloud that maybe was stripped out of this complex structure, attracted by the black hole, and is going to be destroyed in some decades, or something different. Is there a star inside? We don't see any for now, but it's interesting to understand how this can survive actually in an environment that is so excited by the star presence and so gravitationally important because of the presence of the black hole. So, for example, one question we can ask is this in free fall toward the black hole? Is it on an orbit? Is there really a bow shock? How does it work? Does it interact with some stellar winds? So you can really underline local processes going on there as they happen. Well, 26,000 years ago, of course, because the galactic center is 8 kiloparsec away, but still gives you an information about what's going on and how it is happening. So this all you can do just looking at this very central field that you observe year by year. But as you remember at the beginning, I told you we have another huge data set covering other regions. That it's not taken year by year, but still gives you a high resolution information of what you have, because you have also spectral information on this. So you can build a big mosaic where, for example, you look at brachy-gamma emission line. And here is the brachy-gamma emission line color-coded with blue shifted and reshifted, and you start seeing the shape of the mini-spiral that we were talking about at the beginning. And you can really see, for example, this here you have an extreme velocity in the redshift, and so you can study really the dynamic of the structure. And you can do the same for other lines that you have on the data set, for example, molecular hydrogen, iron, and so on. So this helps you also putting in a three-dimensional context the structure when you know a little bit more about the dynamics. So this is just a bigger picture. These are the fields that we have with Osiris, with VLT. We also have some bigger fields with SPIFFY that covers the whole central parsec, and we can put this all together to try to build a big mosaic that tries to solve the puzzle of the galactic center. And then, of course, I told you this is just brachy-gamma, but you can also look at other lines. Here, for example, you have some brachy-gamma is here. This is the whole central parsec, so it's a bit much bigger field. This is this field here, while what I was talking about before was just this tiny field. But you can see, for example, with brachy-gamma, iron 3, H2, and iron 2. So you can really compare different lines and try to understand a bit more what is going on, what are the local processes going on. For example, over here, in this region that is very close to this spherical structure that we call the mini cavity, there is a very important emission from H2 that is also coming from iron 2 in the same region. So something interesting might be going on there. Maybe a collision from the arms of the mini-spiral that are colliding in this region, or maybe connected to the mini cavity. There are so many things going on in the galactic center. You can underline so global effects, but also local effects. This point I was talking to you before is one example. This is another example, is a star observed with Osiris that shows like kind of an atmosphere of brachy-gamma emission line that also is present in H2. So the question is, this molecular hydrogen H2, is it forming in the atmosphere of this star? How many other lines are present in there? How does it work? How does it evolve? What is its velocity? And so on. So there are many things you can learn. And this is just very quickly, I showed you we have this tool that is a three-dimensional visualizer for these cubes. And sometimes you need something more. So you need, for example, to make a fit with the emission line of the gas emission that you want to study. And a nice way to do it is using a global fit that takes into account all the spectra at the same time, so you don't do it pixel by pixel, and basically take into account the fact that what you observe is basically smooth. So you want to put inside the fact that pixels that are neighbors are correlated. And when you put inside this information, you can have a fit that is much smoother, and you take into account the fact that these are structures that are not point sources like the stars. And the results can be something like this. So this is the emission from molecular hydrogen for different lines, and this is the flux, the velocity, and the width of this line you get from this fit. And you can also apply to the inner field of the Lazarus field, and this way you can more easily disentangle components, because the problem is again the crowding. So you have the stars, the gas, the compact features, and also the extended features all mixed together. So you need multiple tools that helps you divide all these things, disentangle them, and study them one by one. This is just a very quick overview. If you want, we can talk more about this, but I didn't want to make this too long. So let's get to the conclusions here. So I showed you mainly one tool, the Astrofísica tool, that helps you understand the three-dimensional cube all at the same time. You can turn it, you can cut it, so you can really follow all the features that you're interested in. And very quickly, I just show you this three-dimensional fit that helps you get the extended features in a very nice and clean way. So thanks to these tools, you can disentangle many current features that change in shapes, that moves, that change velocity. And of course, the next step is try to understand what these are. Are those all the same origin, or does come from different origins? So for this, we can try to fit orbits to them to try to understand if they are interacting with other material, they are tidally interacting with the black hole, they are accreting on the black hole, what is going on with them. So there are basically two interpretations for these compact objects that I was showing you for the main part of the talk. They can be dusty compact stellar objects that are like this G source that the galactic century people are talking a lot about, that we think now is kind of stellar objects surrounded by a lot of interstellar material, or they are just gas clouds. If they are gas clouds, so no stars, no stellar thing inside, are they pulling and they are going to accrete on the black hole? In this case, they can help us understand more on how material accreted at what rate to the supermassive black hole, or are they going to be blown away by Sagittarius A star outwards? What is going on with them? So this is, in general, to understand better this region that is very complex. Everyone has to do with small parts. Someone is doing the stars, someone is doing the gas. But we want to try to put all the pieces of the puzzle together, and studying the interstellar medium, you can understand a bit more about the three-dimensional structure of the galactic center, and you can try to just put in evidence small and large scale things that are going on there, try to understand a bit more how this complex but exciting environment works. And this is the end, so I thank you very much for your attention.
I'd like to know more details on the Sagittarius A outflow because of my ignorance. I mean, I don't know anything about that, so I'd like to know about the energetics of such an outflow and the size in which you detect that, and in which lines or in which wavelengths. I mean, I have no idea about that, so please.
I'm not really a specialist about that. The question is to see here if there is an interaction with the outflow from Sagittarius star, or if they are accreting on supermassive black hole. About the outflow, we don't really see in this field and in these lines. I think you see well these bubbles, and well, probably Reinhard knows more about the outflows from Sagittarius star. But in this field, at these wavelengths and with this resolution, we don't really see an outflow coming from it. So in the near infrared and at this scale, we don't really have any trace of outflows coming from the black hole itself. We don't even see any material actually accreting on it directly. So maybe we don't have the resolution yet. Maybe there is nothing to be seen there in the near infrared, but it's kind of still very hidden, at least in this band, I would say.
Yeah, I don't remember the details, but I think 1 or 2 years ago, in a talk from Rainer, I think, was the mention to one of these clouds, which was already about to fall into the black hole, to be completely disrupted by the black hole, and people were expecting which kind of reaction could come out from this. Has this been observed, or is expected to be observed? How is?
So I think what you're talking about is this G2 source that I was mentioning. mentioning before. So I think it was in 2012, everybody was expecting it to pass to its closest approach and so interact with the black hole, like basically getting destroyed with fireworks. That actually did not happen. This source survived the closest approach passage, and that's why we think there's actually a star inside it that keeps all the material together and prevented it from being completely disrupted by the tidal forces of the supermassive black hole. We don't see very well G2 in this data because probably the signal to noise and the spatial resolution is not high enough. We have some hints of it, but it's much harder to follow. Not in the nice way we did with other blobs, but what I know about other complications and other bands is that you actually see it survive pretty nicely without any fireworks after the passage to the closest passage to the supermassive black hole, unfortunately.
Already estimated an orbit for X7 for this stretching cloud?
Because the tricky thing is that it's not a point source.
Yeah.
So what do you use to trace its
But if you just by eye extrapolated, when does it hit such a star?
We have done very rough calculations that I'm not very sure
years,
about.
5 to 10 years?
I think it's a bit more from the calculations, but it's a bit hard to understand and make a proper calculation, so maybe L-band images is going to be better, so I'm waiting for that. Also for the velocity, it's very hard to understand what is the velocity we have to follow when you look at the spectrum, right? Because, I mean, it's a resolved feature, so maybe this is the head of your thing, and so you just look at this one, then it's slowing down. I don't know, it's a bit tricky. I think this one has to be studied with some care.
So actually this is very exciting now because what Anna is seeing there, and we also see it in L-band images, so we try to work together on that. We really think that this thing there is actually a cloud, and that it's obviously being tidally stretched. This thing that you mentioned at G2, it was said it was a cloud, but nobody ever knew, and apparently it's not a cloud. But here there's no stellar count, there's really no star probably, and we really see already the tidal stretching contrary to the G2, so this looks very interesting.